So it's really a pleasure being here. It's just beautiful, and have been having some wonderful conversations over the last few days. And I think Kerry was asking me how these group discussions were going and so on. I think, you know, one thing that definitely happened was that these discussions made me change my slides a little bit. And in particular, if you notice, I added this "on your laptop" after my title, because a lot of the discussions I was having with many of you here was, all right, you know, Bayesians have been talking about, or statisticians more generally have been talking about big data and modeling and so on, but are we really talking the talk, or are we actually walking the walk as well? So in terms of actually doing some analysis, or is that all computer science and so on? So I'm going to try to basically focus a bit on the computational side and how statistical models can in fact be very, very useful in doing computations and inference for big data. So let's see if I can use this. Okay. All right. So first, so this is joint work. Well, this is not one project, obviously. I've tried to make this a bit of an overview talk and borrowing from recent or current projects going on with Abhirup Datta, a former student of mine, now at Johns Hopkins University, a wonderfully talented young statistician. Lu Zhang is one of my current students at UCLA, and Andrew Finley is a well-known statistician and, well, spatial statistician, and also a forestry and geoinformatics researcher at Michigan State University. Was many years ago my student at the University of Minnesota. So just to give you a very quick idea, or just a quick introduction into what types of data sets spatial statisticians are nowadays encountering, here's an example from the state of, the beautiful state of Alaska in Tanana Valley. And if you are, oops, I did something wrong. I need to get better at this. Do you know which one is the pointer here? Oh, this one. Okay, here you go. Thank you. So this is the state of Alaska. Here's Tanana Valley. And if you zoom into this part, this is what we get. And just to give you a very quick idea, particularly in forest management and you know, in biomass research and so on, nowadays folks are actually trying to look at high-resolution prediction maps for forest height. And you see these red lines here. These are, in fact, what are like LiDAR flight paths. It's a very recent remote sensing technology. You can look up Wikipedia for more details on that. I've written quite a few papers on LiDAR data and how some attributes of that. Won't get into the details of that. But you have a lot of observations coming from remote sensing, and as well as from you know, surveys from forest. And this gray zone that you see is essentially a forest canopy height. So that gives you basically a tree cover, an idea of how much coverage of tree there is, and that the more trees you have, that's better for sustainable bioeconomies and so on. Then on the right-hand side, you have a map where you actually have some history of forest fire. So these red patches basically tell you whether there have been a forest fire within 20 years or not, and you could have certain areas of interest, such as 1 and 2 here, where you basically want to focus on and try to understand the impact of forest fire on forest coverage. So the key point here is that this is a massive data set. It has about 10 million locations, and you want to probably try to analyze this, accounting for spatiotemporal associations or so on. So I'm going to focus mostly on the spatial association. You have a fantastic talk coming up later by Noel Cressy where he's going to talk more about spatiotemporal. And spatiotemporal is indeed exceptionally important. And we've done spatiotemporal work in big data as well. But since I want to get to the computational bottlenecks, I'm going to keep this a little simple and try to look at focus only on the spatial aspects, mostly on the spatial aspects. But before spatial statistics, you actually ask yourself a more simple and fundamental question. All right, if you have a data set that has like 10 million observations and you have, say, for example, a few covariates, how can I even analyze or fit a simple Bayesian linear regression model to that data set on your laptop, for example, all right? So let's go back to the very fundamentals. And you can, if you look at any Bayesian textbook, I, for example, use Christian's Bayesian choice, and also David Dunson's the BDA3, or Andrew Gelman's and David Dunson's and a host of other authors, and you will find this beautiful little model. And it's the most fundamental Bayesian linear regression model that we know because it has exact it gives us exact inference. You can work out the distribution theory very easily. What it says is that, well, you have yi given beta and sigma square, independently normal xi transpose beta, sigma squared, and then beta given sigma square has a conjugate prior. The important thing is to bring in the sigma square, scale it here with an inverse gamma, so this becomes a normal inverse gamma family, and everything works out beautifully. I see many students nowadays, actually go into a lot of fancier stuff and do not worry about these models. They think these are restrictive and useless. But I'm going to make the point that sometimes it's actually good to come back to the basics and try to keep things simple and perhaps even use it. So for example, if you have a situation where you have a huge amount of data and you even want to fit the simplest Bayesian linear regression model that you can think of, well, you have exact Bayesian inference here, right? Sigma squared given y, beta given sigma squared y. You have these quantities, small m and capital M, a few matrices here and there, a few vectors here and there. The two important quantities, I like to call this the M&M formula. It comes out like this. The uppercase M is the variance covariance matrix, is the precision, and the lowercase m is this guy here. If you compute these two, then the rest can be computed. These are the only two quantities that you don't know. But here's the question. All right, simple model, not even spatial or anything, right? But simple linear regression model, but how can I actually analyze this if I cannot even load the data into my available workspace? So there are different approaches to this, but if I don't want to, if I just look at this model, there's a fairly straightforward way of trying to do this, which is that if I actually partition the data, split it up, all right, into different subsets, I analyze each subset differently. I mean, with this model, fit this model to the different subsets, I can exactly recover the full posterior. There's no approximation, no MCMC, nothing. I can simply get it back. There is in fact, in computer science and machine learning, you have this famous framework. Some of you probably, perhaps all of you have heard of this, Hadoop. And it's called this MapReduce framework, which is kind of another way of saying divide and conquer with some resources in cloud computing. The cloud part comes in only because you have to store the data, and you just cannot perhaps not store the data on a hard drive here, or even if you are able to, it may become more complicated to take chunks of the data or read chunks of the data efficiently in an interface such as R or Julia or something like that. But before you go, wow, this is all computer science and so on, well, there's actually statistics here, because if you do your fundamental distribution theory, and again, this is almost like a homework problem that I give in my class, you can work this out very easily. You partition the data into capital K subsets such that each size of the data is something that you will be able to manage with the resources in your laptop. And for each subset, you compute these quantities. And then all you need is you can get back the M and the capital M in that previous slide for the full inference by simply doing these simple linear calculations. And so this is all fine, and you can do this in a distributed framework if you're fancy, and you will do this in a matter of milliseconds, or even if you are completely lame in computing as I am, for example, you will probably repeat this and it will take you a little bit more time, but that's still okay. You can at least do the analysis. Obviously, the reason this works is because there's this independence here. So in other words, each partition, therefore, will be independent of each other, and that's why this distribution theory works out nicely. This calculation works out nicely. But this sort of approach is used widely, in fact, in big data analytics. In fact, if you look at some of the big data companies such as LinkedIn and Yahoo, they sometimes do analysis where they fit Bayesian regression models, but for massive data, terabytes of data, and so therefore they actually use Hadoop and try to fit this. The point I want to make here is that there's computer science. Of course, we need them because we need this technology to be transported and in a seamless manner into our laptops, and it can be done. You can take a Google or YouTube video and you can see how to set up Hadoop on Ubuntu or Fedora. I'm sure it can be done on Macs and PCs as well, although I don't know how to do it. But this is not enough, and especially not suitable for spatial random fields because that independence is lost. So there is a line of work where what happens if this is dependent, and how can this sort of simple idea be extrapolated to spatiotemporal or spatial statistics. And I have a paper with one of my former students, Raj Gohniagi, in Technometrics, where we actually attempt that. And the idea is to actually try to find the best, calculate the posteriors from each subset and look at a convex combination of these subset posteriors closest to the full posterior. This is very, very machine learning. These are known as meta posteriors. There's a volume of work by Minsker. Dunson has done some work. I mean, David probably has worked on pretty much everything, right, David? So he has some work on this as well. But it's still not satisfactory fully satisfactory for spatial context. And I'll explain to you why. Let's get back to the very basics of spatial modeling. So you have your forest height outcome. You have let's say an intercept. You have a covariate here, which basically gives you a surrogate for whether how much tree coverage there is, and then you could have an indicator function as whether that area or that location was affected by a forest fire or not. And then what you do is you actually introduce this component here, the spatial process, all right, and then you have noise. And this is probably the most important structure for spatial statisticians. It's a most widely used mechanism is the Gaussian process because we love our multivariate normals, and they're more tractable, and they're specified through a covariance function. Here's, if you want to know more about the history of geostatistics and how the spatial process really comes into play, and this importance of this covariance function, well, here's Noel's excellent book, and then a follow book by Michael Stein as well, where you can find a lot of details on that. But this is what excites spatial statisticians the most, this process. And we want to understand and learn about the process. We want to interpolate or predict across the domains using this process. We want to quantify uncertainty for this process. That is the underlying underlying mechanism that is generating the spatial autocorrelation, underlying mechanism that is generating perhaps the way the data appears, emerges. So that's what it is. And this covariance function leads to essentially a multivariate normal likelihood, looks like a linear model with a variance covariance matrix that is a convolution essentially of these two processes, the spatial process, and then you have the residual process after accounting for the spatial process. And if you just look at measurement error, for example, then you will basically have a structure like this. This matrix is a sum of a covariance matrix plus what is called the nugget effect, or the nugget here, tau squared, and that. So that's what goes on. And of course, that is a simpler version. If you want to really look at LiDAR data, so on, the modeling becomes more and more complicated. For example, there could be the field observations, and especially the LiDAR signals, they themselves could be high-dimensional signals or vectors. And so therefore now what you do is you stick in a little bit of a sort of a factor model here with loading matrices that do some kind of dimension reduction by weighting the processes or projecting these processes onto certain lower dimensional subspaces. But the key point is now, you still have processes here that you need to learn about. And here's, for example, a very simple example. We have this paper in Sinica which has the details. I won't make the modeling more complicated than this. But basically, you're modeling the LiDAR data using a fairly straightforward spatial factor model. And then you have your field observations, which can learn from the LiDAR observations as well using a common factor or a common underlying process, and then an adjustment that could come from lack of goodness of fit and as well as measurement error. And so you have these two processes to adjust for that. This is a fairly flexible model, and this can still be fitted using MCMC and so on. The key point here is, however, not so much the high dimensionality of the Z and the Y, which can be taken care of using these loading matrices and some sort of principal components, but the high dimensional aspect in spatial statistics really comes from this process and the number of locations. For example, in other contexts of big data, we do not have usually a very large number of predictors. In fact, we do not want a very large number of predictors, because if you have a very large number of predictors, then there's little for the process to do. You start overfitting, your predictive performance suffers, and so on and so forth. So our big data or our high dimensionality really comes from the number of locations. And here's the crux of the problem. I'm not going to, I'm going to keep this modeling very simple. I mean, in fact, you will see nothing but the multivariate normal distribution here, frankly speaking. And here's your multivariate normal likelihood. If you want to have the Bayesian extension, you have priors on this beta and the process parameters here. And essentially, I'm going to talk about fitting this or computing this. But in order to compute this, I have this structure here, this k theta. Now, as I said, spatial statisticians get most excited about the process. And the process is quantified by a covariance function. And that's where a lot of the fun lies. I mean, you have these wonderful covariance functions. You can introduce anisotropy, non-stationarity, all sorts of things. The result is you get extremely flexible models, but you do not really have necessarily a computationally exploitable structure for this k theta. Inherently, there is no sparsity. And this is, mind you, irregular locations. You don't necessarily have a grid, as you saw in the map in Alaska. They're very irregular. And it is not completely trivial or straightforward to simply plug in zeros into that. For example, if you just took the approach that I'm going to simply plug in zeros when the distance becomes too large, well, you may lose positive definiteness. The process is not going to be valid anymore. The inference completely falls apart. So we have to be a little thoughtful about how we are going to compute this, because in this previous example, this matrix would be 10 million by 10 million. And we are doing 40, nowadays it's not unusual to get spatial data with tens of millions of locations, all right? 20 years ago when I was doing my dissertation on pretty much modeling similar to this, the largest data set I actually analyzed was something like 800 locations or so on. And now we are looking at a completely different scale. That's what's happened with computing advances and so on. So in order to, oops, I'm sorry, I keep, okay. So in order to compute this, since we need the determinant as well as the inverse, the usual strategy, if this was manageable, would have been to take the Cholesky decomposition. There are reasons why the Cholesky decomposition is so popular. First of all, of course, we like it in statistics because I will also show you that it has some nice connections with the precision matrix. But even besides that, it is one of the most numerically stable matrix algorithms that you can find in order to decompose large matrices. And it is cheaper than it is a direct method rather than the iterative methods such as singular value decompositions or eigen decompositions. So therefore, it is a direct method. So if it can be implemented, it actually is great. It's not an iterative method. Obviously, it's expensive, and that's where the problem lies. But once you have this, computing this guy is really easy because you just do some triangular solving of equations, and you can simply compute it linearly after the fact that you have computed this guy. And this is the main challenge, all right? So that's what basically I'm going to be focusing on, how to actually make this tractable. There's one more important thing to keep in mind, which is prediction and interpolation. And again, simple distribution theory, multivariate normal, nothing more than that. When we want to predict at arbitrary locations or time points, you basically need this conditional predictive density to exist. This is why we need a process. I sometimes get this question, which is a very valid question, by the way, from those who are outside of the spatial world. Why do you really need processes? All right, why not do this in a finite distributional setting and use a lot of the stuff, say, for example, like Lasso and others to probably do big data? Well, this is crucial. I mean, you will need to interpolate across the entire domain. All right, we need to produce continuous maps. And if this density does not exist at arbitrary points, the whole inferential mechanism falls apart. So what the stochastic process enables us to do in a very simple modeling aspect, rather than the measure theoretic aspects of Kolmogorov's consistency, is to ensure that this conditional density will exist for every arbitrary point in my inferential domain. And once this exists, well, I am legitimized in using the conditional expectation, which we love in statistics, and the conditional variances to get what is called kriging, to get predictions. And if you're a Bayesian, you would go one step further and average this conditional predictive density over your posterior density. That's what you will do. And you compute this integral by, again, sampling from the posterior and then sampling from this conditional predictive density 1 for 1. That's basically all there is to it. So the problem primarily is this. And then also here, as you notice, this massive creature is once again raising its head. So that k theta inverse is going to be there. All right, so perhaps the most ubiquitous approach to solving the massive data problems in spatial statistics are these low-rank models. And I think these have obviously attracted the maximum amount of attention, and there's good reason for that. There's, by the way, an excellent review article by Chris Weichel in the Handbook of Spatial Statistics in 2010 on Bayesian low-rank models. There's been a lot of people who have worked in this domain. It'll be impossible for me to really do justice to a full literature review on this, but I'm going to connect this to the Bayesian hierarchical model because it's very natural. In fact, all Bayesian regression models are inherently low rank. You have y given beta z theta tau is normal. All right, this looks awfully like a linear mixed model with this random effects following a normal with some structure. The prior on the beta follows some structure. The process parameters that you have here, theta, that get into this sort of a basis matrix, gets a prior. And that's your hierarchical model, all right? Now, I'm not in the scaled normal inverse gamma family anymore, but that's okay. We are fairly comfortable with this today. But of course, it won't give you exact closed form distributions necessarily, because we're in a slightly more flexible setup. So perhaps you will have to do some kind of MCMC or INLA or variational Bayes, if you like, that sort of thing. So again, this is basically the joint posterior from this. And then what is this B theta? Well, how do we construct this in spatial statistics is we start with the parent process, and then we construct a sort of a low rank process out of that using a set of basis functions. And this is where, you know, the trick comes in. I mean, what types of basis functions are we going to use will depend upon the application It's specific to the application and how we use it. But once you actually take or decide to fix the number of basis functions at R, for example, which is much smaller than n, then you have a tall and slim B theta matrix. And just like we don't worry about the length of the X matrix rather than the width, similarly, the B theta matrix is long, but it's not wide, and therefore the computation works out quite nicely. In fact, it's again the very, very widely deployed Schurman Woodberry Morrison formulas, discovered and rediscovered through the ages. I once took a lecture from C.R. Rao, and he said that in the 1960s or 50s he thought he had discovered this beautiful formula, only to find out that it existed 30 years earlier. I once met Adrian Smith, who was co-author of this Lindley and Smith paper in 1972, and he said exactly the same thing to me, that, you know, I thought, oh, I had this beautiful derivation of this wonderful formula, and then I discovered C.R. Rao had discovered it, and I told him, well, actually C.R. Rao found out that it was discovered by someone else, and so on. So there's a nice history of this formula if you're interested in with the Wikipedia page of how it came about. But it is hugely widely used, and the reason why it is used is that on the left-hand side you have this n by n matrix, and this could be a diagonal or sparse. The B theta is long but not wide. VZ is R by R, so it's not a big matrix. And so to compute this n by n matrix inverse, you only need an R by R inverse right here, and a diagonal matrix or a sparse matrix inversion here, and you're pretty much done. And then there's a companion formula for the determinant that also says that you only need to compute determinants of an R by R matrix, perhaps a diagonal or an easy matrix, and perhaps an R by R matrix, which is a small matrix, again. So that's pretty much it. The nice thing about this in the Bayesian context is there's a very nice Bayesian derivation of this, which was from Lindley and Smith, but actually Chris's book also has this in probably an exercise or something, if I recall. Just take the variance of y in two different ways from the previous model, and you will find this. Now, when you are looking at millions of observations, though, you have to be a little careful in actually computing this. For two reasons. Again, there is a numerical linear algebra aspect to this, because you want to avoid propagation of numerical error when you do these matrix computations. And especially there are some of these matrix multiplications, in particular this part, the B theta, then this quantity inverse times B theta transpose, that can get annoying when you have millions and millions of locations. So there is a way in which you can actually use these optimized functions from Lepak and Blast libraries, an optimized Cholesky and an optimized triangular solve, to minimize the effect of matrix multiplication by doing a little bit of algebra. And I have that described in a paper in Bayesian analysis in 2017. It's okay for a lot of purposes, but you never know, because it depends upon the configuration of the spatial locations and how close they are. The complexity is approximately order of n r squared. R is the number of basis functions. It's linear in n, which is in the millions, and the basis functions is really up to you. I mean, you know, you will probably take as many basis functions as your laptop can handle, for example. Now, I've been using the word laptop. Now, I'm certainly not suggesting that all big data analysis should be done on laptops. Absolutely not. But the point I'm trying to make is scalability, and of course, you can scale up. There is, however, some issues with low-rank models. And one of them is that they tend to over-smooth. And the idea, and the reason, rather, that they tend to over-smooth can be explained using basically a same reasoning as to why you get smoothing in regression. But let's take a quick look at this picture. Let's suppose you have a true spatial random field here generated in a computer. You fit the full Gaussian process. This is not a big data thing. We need to fit the full Gaussian process. So I could handle 2,500 locations. Look at this. This almost emulates the entire field. This, of course, has been evaluated at a sampling of locations, and yet we are able to capture the spatial clustering and get back to this. If you use basis functions with, let's say, 64 basis functions out of where you're handling 2,500 locations. In a number of cases, you see this sort of a bit of an oversmoothing here. And the reason this happens is because you're essentially taking an infinite basis expansion for the full Gaussian process. There is something called the Karhunen-Loew expansion, and you're basically truncating it. You're basically truncating it. So therefore, there's a residual to that approximation itself. And so if when the projection happens, there is, of course, this part of the projection. This is a very well-known, one of my favorite formulas in linear models. You know, you take a column space of B1 and B2, the projector decomposes beautifully into the, as per the orthogonal decomposition. And so there's this residual part. And this residual part is lost in the approximation because you're using a finite number of bases. But there are ways in which you can actually get to the variation of this. But even if you do, sometimes it's not enough to avoid this oversmoothing. Now, I should also say that this oversmoothing is not necessarily a bad thing. It's a different model. Many people don't care about this. But in a context where I actually started rethinking about big data, I was in a situation where we wanted to approximate this random field because this random field was becoming an input into another computer model in forestry. And my collaborator, Andrew Finley, really insisted that this was not good enough. And we were actually trying to improve on this, and we were successful to a certain extent using low-rank models. But when we went into millions and millions of locations, we were, hitting roadblocks. Now, there are fixes and improvements, as I said. For example, Matthias Katzfuss has a wonderful paper in JASA in 2016 where he basically uses this predictive process and recursively approximates this residual part and gets close to this. But there are issues here in terms of the implementation because he has partitioning and he has to take subknots, and if the knots become, subknots become close to each other, then you start getting into singularity problems. So it is not as effective in terms of massive data sets, especially if you have a lot of locations that are close by. Another option is to take the Havard-Roux route or the sparse approximation route or even the covariance tapering route and try to introduce sparsity-inducing processes, which is what I'm going to turn to in a second. But do keep in mind that these low-rank models are amazingly flexible and still used widely, especially because they work very well with non-stationary random fields. There's a natural way in which the resulting models become non-stationary and they're able to capture much of that. So when we actually came to that issue about emulating the random field in millions of locations, I turned back to a paper in 1988 by Vecchia, which in fact in a couple of earlier papers of mine I had criticized. And it was not my first choice, frankly speaking. But then I delved deeper and tried to make something out of it, and now I think it's quite useful. So here's what Vecchia did. Vecchia took a multivariate normal density and said, I'm going to take the locations, simply use an arbitrary ordering of it, write it as a product of these composite densities. Okay, that's the exact decomposition, probability of WL1 and probability of WL2 given WL1 and so on. And then I'm going to approximate it by not taking the entire history of it, but simply taking what is like essentially a directed acyclic graph. The parent set gets shrunk to some kind of neighbors. And this becomes a composite likelihood, and I'm going to use this as an approximation for this to, in fact, estimate the parameters theta here. That's what Vecchia did. So it was a likelihood approach, and one of the reasons I was not too enamored of it was because it was not doing or serving me well in terms of inferring on the process. There was no process here. As you can see, it's just a likelihood approximation on a finite dimensional distribution. It's not even clear how I can do predictions from this, for example. So Abhi Datta came along, and I presented this problem to him, and I said that, there's a way in which I think we can work out a process out of this, and let's see how that works. And, as often happens, a very simple extension to Vecchia's actually throws open the door. And one very important thing we found, very easy actually, it's really quite easy to work this out, was to do this additional step. This approximation itself is a multivariate normal distribution. What else can it be? I mean, once you're in the joint multivariate family, you do conditional dependencies, independencies, you're still in the multivariate normal. The nice thing, though, is that this k tilde theta is, in fact, available in closed form, well, up to the covariance function, but its inverse is sparse. The structure, again, is available in closed form up to the covariance function, that is here. With only at most n m squared non-zero entries. And I'll call this k tilde theta, therefore, as a nearest neighbor approximation for k theta. So if you are actually in the world of Gaussian graphical models, there's a very, very nice interpretation for this. Basically, again, you take a joint multivariate normal density, write it out like this, and then simply express each of these conditional densities as a linear model. And this is what I do. And as David Dunson was giving a talk in my department in UCLA a few days back and said that all Sudipto does is find some linear algebra to do in everything that he does, linear models, and he's absolutely right. I had to get into this and say, okay, where can I do some linear algebra? And so bingo, here's the linear model that is there. And it's quite nice because you have this eta, which essentially is I minus A times W, L is I minus A, is lower triangular, and look what it does. The L is essentially the decorrelation transformation. So in other words, it makes this decorrelated. The moment I make or force some of these Aij's into 0, I introduce conditional independence and therefore sparsity. Sparsity because of this L. All right, so in other words, this is a very nice way to introduce sparsity in the lower triangular part of the Cholesky decomposition. All right, and this idea was in fact used in a different context yesterday in Gary's talk on the VAR models as well. So it's not something new. In fact, if you look at T.W. Anderson's classic book on multivariate analysis, he didn't quite use this terminology, but the ideas are there. So here's just a quick pictorial depiction. What is really nice from this decomposition is essentially I've constructed the Cholesky, or I will show you exactly how to do it in a reasonable way when I construct the A and the D, but then I get the determinant for free. All right, that is, the determinant computation is an important computation for full likelihood-based inference, because it's there and I cannot ignore it. Some classical methods or paradigms will ignore the determinant. So for example, you can solve scoring functions and do asymptotics. It doesn't quite work in these domains as well. For those of you who are this generation Z of pseudocoders and like to look at pseudocode more than math, here's what's going on. Here's a for loop. Here's how you construct. You have the K matrix, the original covariance function, how you construct the A and the D. So essentially how you construct the Cholesky decomposition. Well, you take the parent, for each I, you take the parent set, form the parent set, that will be the neighbors. You solve m by m. If you have m neighbors, let's say m is 10, 15 or something, you just solve a 15 by 15 or 10 by 10 matrix equation here, linear equation here, and then you simply do a dot product, which is essentially calculating the Schur's complement and gets the conditional variance for the diagonal D. So we need to solve n minus 1 linear systems, but each is of size at most m by m. But the nice thing is you can completely override the memory. One loop does not depend on the other. It can be parallelized, or, as I said, if you are in a modest computing environment on your laptop, you just read and override the memory. You don't ever need to store any big matrix, not more than 15 by 15 or 20 by 20. And then the quadratic form comes out, which is for the exponent in the normal density. And that is done recursively, again, using purely linear calculations. And as I said, once you have the D's, the determinant is simply this. So you're pretty much done. So this is really massively scalable. That is the nice thing. And as I said, one advantage it has purely from the computing point of view over low rank models is that matrix multiplication, which should not be ignored because it is a moderately expensive operation with n squared complexity, is minimized. As compared to low rank models where you still need an n by r matrix to multiply with perhaps an r by r matrix. And the number of basis functions when you're looking at massive data sets cannot be made too small. All right, so that was good in terms of likelihood computation, but we wanted to now make this a process. So what is the simplest thing we can do, all right? What is the simplest thing we can do, you know? There's this lowest common factor of publication that, okay, let's look at the simplest idea and see if somebody has already written it or not, and sometimes you'll get lucky that, oh, this is simple and it seems nobody has done it. Well, you know, with people with modest brains like myself, that's a good approach. So let's do that. All right, well, what I need, of course, is to basically have a well-defined neighbor set over the entire domain so that if you give me an arbitrary point, I will still know what its neighbors are. And then secondly, I must ensure that the conditional predictive density, remember that I talked about, needs to exist everywhere. So therefore, I need a process. Okay, so you basically look at a reference set. I call this a reference set. This could be the observed points, and you just collect them in an ordered way. You can take any order. This is one of the unpleasant things about this, which did not make me immediately fall in love with this at first, but let's just indulge for a moment. And then you have these neighbor sets, or these neighborhoods that you construct. You have the empty set for I equal to 1, then you take the past history for a while, and then you simply take the m nearest neighbors of Li from the rest. So when you come to an arbitrary point, you take the set of m nearest neighbors for the location in R, in this reference set. And this actually gives you a way to find neighbors, okay? In other words, all I'm doing is just taking a finite set of points over the domain. It can be as large as you want because its size has no effect on the computation, as I showed before. And then I'm just going to basically search that part to basically locate the locations, or the neighbors of an arbitrary point that you give me. And this completes the consistent extension to a process, because all I'm going to now do is I'm going to use the Vecchi approximation for the realization of the process over the reference set, and then multiply, or keep multiplying, with these conditional densities. And this extends to a process. Probability of WL, L is arbitrary, given this realization over its neighbors, once it's well defined, all right? So basically, conditional on R, this reference or on this realization, I do have conditional independence. But that's okay, because once I look at the marginal covariance, integrating out the WR, it's not independent anymore. And so it's not that the predictions are independent. So conditional independence is fine as long as the marginal correlation that it induces is reasonable. And that is what we found in when we did this sort of thing. And it's massively scalable. Now, let's just take a quick look at a couple of other nice, insightful things about this. So this NNGP has a very close connection with best linear unbiased predictors. And if you wondering what best linear unbiased predictors are, well, there's a beautiful paper in Biometrica in 1999 by Pourhamadi. And then Michael Stein had a paper in JSSB in 2004. Joe Guinness has a nice paper in Technometrics more recently, where they've used these blops, as they like to call it. And basically, I look upon them as nothing more than conditional expectations, okay? So basically, if you see, you have Wi in the ith row of that linear equation. Take the conditional expectation of that. What does it do? It actually projects the Wi onto a subset of these random variables here, right? W1 through Wi minus 1, depending upon who its neighbors are. So there are some undesirable features about this NNGP. First, the bad news. Let me give you the bad news. Well, any optimalities, now this is good. Conditional expectations are beautiful creatures, right? I mean, we all like them. They have optimality properties. They're projections in Hilbert spaces. But any optimality of the resulting distribution in this framework will depend on the order of the W1 through Wi minus 1. That's bad news number 1. Bad news number 2 is that if you take a sequence of models where the neighbor sets are, increasingly sparse, so that means going from right to left, it becomes increasingly sparse, then the Kullback-Leibler distance between the this NNGP likelihood or the Vecchia likelihood and the true multivariate full Gaussian process likelihood is going to keep increasing, obviously, because you're projecting onto a smaller set. So therefore, the point that you will have, the candidate points to be closest, are not going to be getting any closer. All right, so that's a very intuitive result. It's a very beautiful, simple proof. I do not, by the way, know if this result holds for general exponential families, if there is work that has already been done. The proof is surprisingly simple if you actually reformulate. So there's some merit to doing some linear models, because if you use this interpretation, this proof becomes really easy. If you don't, it becomes really complicated. So that's two pieces of bad news. And Guinness, in particular in technometrics, actually used results such as this to basically come up with a particular optimal ordering. I'm not going to talk too much about this, but just to let you know that if you look at the deviance, which is like the Kullback-Leibler, the divergence for different types of ordering of the locations, you can get a little bit of discrepancy. But the overall inference in terms of process parameters like the nugget variance plus the spatial variance and the spatial range is quite robust, and so is predictions. But the real, so that was the bad news. So what's the good news? Well, the good news is that the NNGP, in fact, solves the problem I was trying to solve. Remember the top row? I showed you this. Well, if you actually come back, so this was, I was beating up a little bit of my own work on predictive processes and how poorly it does. You could, as I said, there could be some improvements, but perhaps one needs to think carefully about scalability, especially into the millions. And the NNGP, even when you're doing millions, with 10 and 20, usually gives exceptionally robust inference. Now, for example, in a 2,500 location situation, I saw with only 10 neighbors or 20 neighbors, I was able to get back literally this field. All right. Not necessarily, you might be thinking, okay, but with millions, will 10 or 20 neighbors suffice? And the answer is not necessarily no. Let me put it that way. First of all, it's very difficult to conduct full GP simulations in 20 million locations, okay, because you simply cannot fit or simulate it. But if you do some types of, Toeplitz types of approximations to do fields, our experiments suggest that it hardly goes, you need above 20 or 25. And Michael Stein has a series of papers on the screening effect of kriging in the mid-90s, where he actually talks about why these conditional dependencies can actually be very, very effective as long as you're using the Matern class of covariance functions or some other types of covariance functions that satisfy certain spectral conditions, which I'm not going to get into. Now, once you have the process, the fun starts. What you do is you just think about, okay, here was where I would put my GP, just replace the GP with the NNGP, or for that matter, any other low-rank process if that's what you want to do. That's totally fine. The nice thing is that they lead to valid processes, valid process-based models, and you can do the entire inference on your own. There are two ways to do this. One, for example, right here, in this example that I showed you, simple model, but you could put the NNGP on the process itself, the latent process, or you could put the NNGP directly on the response. I do want to point out that these two models are not equivalent. What this does is it integrates out the WL, okay, you get the full GP marginalized, then treats the Y, the response itself, as the process and approximates. So the latent process, the residual process, is lost, which is undesirable in much of spatial inference. But in case you're looking for scalability, this is much more scalable. And if you do not want inference on the latent process, that's fine. This might actually suffice. But I do not necessarily recommend this model over the other. In fact, I'll show you in a second that this, in fact, performs better than this in most cases. And all this has been brought together under one umbrella in a generalized Vecchia paper by Katzfuss and Guinness that I don't know if it has been published yet, but it's in archive. Okay, let's get back to our good old textbook example for a second, okay? And let's see how much we can do with exact inference. So come back to this. You take the full GP covariance matrix. If you write that as a correlation matrix plus a delta squared times I, where delta squared is the spatial to white noise variance ratio, signal to noise ratio. And what you do is you apply this normal inverse gamma prior on the beta and sigma squared. Well, you come back to this beautiful Bayesian conjugate linear model. You get the predictions in closed form. Fully closed form, no need for MCMC, and everything in linear time. This can be done, and this has been done, by the way, if you're wondering what this is like set of co-author titles, and the B is Banerjee, and the F is Finley, JCGS 2018 plus. We have some different algorithms for NNGP, and this is one of them. Okay, so there's this response model versus a latent model, and we basically said, okay, go ahead, use the response model. Because especially it's more scalable and you can have this nice form here. Well, there's one bad news again. And every time you do something, you try to analyze it theoretically, you will find probably, wait a minute, there's no one solution that is like the cure-all for everything in spatial statistics, I think. So if you look at the distance of the latent model from the full GP, and if you look at the distance of the response model from the full GP, you tend to see that the latent model in fact does better in terms of like being closer to the full GP. And theoretically, though, both are admissible. That means one does not necessarily universally dominate the other in the sense of being closer to the full GP. But what happens is, and if you can do a little bit of matrix analysis to show that the error from the full GP to the latent model, the latent process model, where the NNGP is approximating the latent process, can be written out like the error can be written out in terms of a matrix B and a matrix of order E squared, where E is the error from the Vecchia approximation. And then this leading matrix, using some matrix norms, for example, the Frobenius norms, but there are other equivalent norms that you can use, will be bounded above by the Vecchia. So in other words, you get an order E squared plus an order that is not that is at least less than equal to E. And the E is essentially the error from the response model, so therefore you see the latent model does a little better in terms of the error. So now comes the question, all right, you have the response model, but hey, the undesirable fact is that I cannot recover inference on the process from that. So this is where Lu Zhang comes in, and she basically says, all right, wait a minute, let me see if I can actually recover or the inference on the latent process, all right, using this conjugate framework so that I do not have to do MCMC. I can do this on my laptop. And the trick, again, is to structure the whole model, this model, as an augmented linear model. All right? Sorry, David. Again, I'm back into this sort of obnoxious thing. But this just helps. What can I do? Or maybe I'm addicted to it. So you have the Y star, you have the X star, you have the gamma, and you have the eta. It's just written like this. Here you have beta, you have W. The gamma, you can see this is a very long vector. Distribution theory is beautiful. No worries there. It's statistics from Casella-Berger, essentially. The only problem is this X star transpose X star. X star is now a pretty big matrix, and it's not narrow either, right? Because this W is millions. But the thing that you observe is you never need to work with this X star. You need to work with this X star transpose X star. And you need this inverse, all right? The nice thing is that this is sparse, largely sparse, with a small non-sparse structure at the corner. And here comes our friend Akiro, and he basically talks to Aki talks to Lu Zhang, and they talk about conjugate gradients and how to do this effectively. And bingo, it can be done using RCPP eigen. Ooh, I'm in deep trouble, it seems, in terms of time, which always happens. All right, now, one quick question. To get this going, I mean, do I really need to do inference on the delta squared and phi? Of course, I do not want to completely ignore them or fix them. So I use a cross-validation for that. Basically, I'm going to skip through this in the interest of time a little bit quickly, is you take a big grid, run this model. Mind you, this model runs in a matter of seconds, as I'll show you. So therefore, I can run this many times. I do a cross-validation on a grid of delta squared and phi, and I look at the root mean square predictive error, and I optimize or take the optimal value that minimizes that. So I can do this using a multiple fold cross-validation. Quick result here. If you look at the full MCMC version of the collapsed NNGP, which basically means take the full latent process model, marginalize out the random effects, use a sparse Cholesky decomposition, you have about 319 hours to run this. If you do go to the response NNGP, where your inference is limited, that the process is lost, the latent process is lost, you get pretty much robust inference, almost, and you can do that in 38 hours for these parameters. If you go to the conjugate NNGP, by the way, you can still get these credible intervals for all of these guys except for the phi. The phi is kind of optimized and fixed through that cross-validation algorithm. But everything else, you have the credible intervals. I just was too lazy to fit this using my LaTeX tricks into this slide. And they look pretty similar, not too dissimilar from this. Slightly narrower, perhaps, because of the fixing of the phi in some sense. But you basically get that, and you can do this in 7 seconds. In Andy Finley's laptop, which I think is a little fancier than mine, in mine it takes about a minute and a half or so for 5 million locations. A quick graph here for the computational runtimes. There are different NNGP algorithms. Again, you can find this in the JCGS paper in detail. This red one is a sequential vanilla Gibbs sampler. No marginalization. Go for the full latent process updates. You get closed form Gibbs sampling updates, kernels, but it's slow to converge. The process parameters are usually quite hopeless. They are not asymptotically consistent, and therefore the effect of the prior never goes away. But in terms of time and as a function of CPUs, you can see the big point is that the response model and the conjugate obviously do much better and faster. So if time is of essence to you, you actually can do that. And here you have up to 10 million, and this is the benefit you get from the computational time. So just quick concluding remarks. We do have an R package, SPNNGP, that will do this for you on a modest computing platform. If you want to do this for millions, you will need a little bit more machinery, especially in terms of a very efficient access to loading the data from a cloud system or a big server and communicating with that server. If you have multi-processors, go for it completely. It will make life much faster for you again. This is agnostic to any specific algorithm. All right, this is a model-based solution, as I keep saying, and so you can do Gibbs, you can do random walk metropolis, Hamiltonian Monte Carlo, variational Bayes, INLA. If you can probably, some of you, probably the younger generation will do this in their head. You don't even need a computer, right? Maybe, I don't know. If you're doing multivariate geostatistics, you can do matrix variate normal inverse Wishart families. Beautiful distribution theory. Go back to the basics. Don't throw away the good old textbooks. It's not just about complicated distributions. It's sometimes the fundamentals are important. Many challenges. I pointed out some weak points about the NNGP. Non-stationary models continue to be a big challenge, although I think low-rank models are perhaps better, and I think Noel will talk about that, and you will see some good stuff there as to how spatial statisticians really solve some challenging problems. I'm going to, there is a Hamiltonian Monte Carlo implementation of the NNGP, which, by the way, is not computationally too efficient because it's been coded up entirely in Stan. But if you want to see a working example of how to get this running, here it is. You can take a look at that, and if you can run it in Stan. I have some selected papers. Just one quick point I do want to mention is there is a space-time paper here, this 2016 paper in Annals of Applied Statistics, which actually talks about NNGPs on space-time, and space-time is a different ball game altogether. And the one point I will mention is that we were selecting neighbors. Neighbors in space is one thing. Neighbors in space and time is a completely different thing. Neighbors in space need not align with neighbors in time. So this sort of simplicity is not going to work. There we had a slightly different approach where we were learning about the neighbors over time. We had to do that, but that can also be done computationally efficiently as long as the covariance functions you're using satisfy a pretty regular or generic monotonicity condition. So there's some of that as well. So on that note, can I just make one quick joke? 1 minute. Sorry. I was giving a talk on similar lines in NCAR, National Center for Atmospheric Research, and Doug Nitschke, who's one of the exponents of climate statistics and spatial statistics, said that, Sudipto, I love Bayes, but I don't like MCMC at all, and that's why for this big data, I just don't know what to do. Now, since this is a Bayesian conference, I'll say this. I asked Doug, so Doug, what are the types of problems you're actually trying to solve? And why is it that you don't like MCMC? They said, MCMC takes so long, I have to wait for 7 days to get my output. And what are the problems you're trying to solve? Well, I'm trying to predict the weather 100 years down the road. So I said, wow. So you want to predict the weather 100 years down the road, but you can't wait for MCMC for 7 days. Didn't quite gel. But thank you so much. So, yeah, go ahead.
Yeah, just a small question.
Yes,
Sudipto. Great talk. Thank you.
Thank you.
Just to add an extra component, which I know you're onto, which is the multivariate aspect. Going from space to space-time introduces neighborhood structures that aren't obvious, and then you're into multivariate. Could you say something about that? Thanks.
That's absolutely another layer of complication, and the model I presented briefly here is in fact a multivariate model, and the question becomes, well, now you have a cross-covariant structure rather than the usual covariance matrix, and I do not. There are a couple of different ways in which you can actually do multivariate modeling with NNGPs. One would be to build the model conditionally, like you have posited in your Biometrica paper. And the other is to use a latent process approach, which is more like originalization. But if you really want to do this most generically, there is a way. Do I have a I don't think I have time to do some chalk stuff, but what you can do is you can take the Vikia, and this is actually kind of interesting because you can, just like you do high-dimensional covariance matrix estimation, you can take that whole set of random variables as one large set and build conditional independence there as well. I haven't done that there. I have some notes, and the math does work out, but there are some issues. So it's, yeah. Thank you.
I think we stop here for the moment.
Sure. Thank you. Thank you.